There is an altitude band above every flight you have ever taken, above the weather, above the ozone layer, above where any commercial aircraft has ever operated, where the physics of flight, as you understand it, completely breaks down. At 100,000 feet, 30 kilometers above the surface, the air is so thin that a conventional wing generates no meaningful lift. A jet engine cannot sustain combustion. The sky above is not blue, it is black. The temperature is approximately -60 degrees Celsius, but not because of altitude, because of solar radiation geometry. And yet, the United States government has operated aircraft in this environment since the 1950s. Classified aircraft, aircraft whose existence was denied for decades, aircraft whose physics required solving problems that the scientific community publicly said were unsolvable. The U-2, the SR-71, the X-15, and programs whose names remain classified today, each one operating in an environment where every rule of conventional aviation no longer applies, and each one requiring a completely different physics of flight, physics that was developed in classified laboratories, tested in classified facilities, and is still only partially understood in public literature. Let me show you what happens to physics at the edge of the atmosphere, and what was built to survive it.
At sea level, the atmosphere contains approximately 1.225 kilograms of air per cubic meter. That density is what makes wings work. That density is what turbine engines compress and combust. That density is what creates the sound barrier that defines supersonic flight. At 100,000 feet, the density is 0.0001 kilograms per cubic meter, 1/10,000th of sea level density. The physical consequences of this density reduction cascade through every system that makes an aircraft fly. Wing lift is generated by the pressure difference between the upper and lower wing surfaces, caused by the deflection of air molecules passing over and under the wing. With 1/10,000th the molecules to deflect, a wing the same size as a commercial aircraft wing generates approximately 1/10,000th the lift. To generate sufficient lift at 100,000 feet, you need either wings of impossibly large area, impractical for a high-speed aircraft, or you need to fly so fast that even the tiny number of available air molecules creates enough dynamic pressure to support the aircraft. The SR-71 Blackbird solution, fly at Mach 3.3, 3,500 kilometers per hour, at 85,000 feet. The dynamic pressure of Mach 3.3 at that altitude generates approximately the same aerodynamic forces as Mach 0.5 at sea level. The aircraft was not defying the physics of thin air. It was compensating for them with kinetic energy so extreme that the airframe heated to temperatures exceeding 300 degrees Celsius from aerodynamic friction alone. The physics did not break. They demanded a price, paid in material science, propulsion engineering, and heat management, that took 20 years of classified development to afford.
The SR-71's operating altitude of 85,000 feet is extraordinary, but it is not the boundary where physics becomes genuinely exotic. That boundary begins at approximately 100,000 feet, where the atmosphere transitions from the stratosphere into the mesosphere, and where a phenomenon called aerodynamic heating transitions from a materials challenge into a fundamental physics problem. At Mach 5, 5 times the speed of sound, the air in front of a moving object cannot get out of the way fast enough. The molecules pile up in a compression zone called the bow shock, a standing shock wave that heats the trapped air to temperatures that no known solid material can survive indefinitely. At Mach 5, bow shock temperatures reach approximately 1,500 degrees Celsius. At Mach 10, they reach 5,000 degrees. At Mach 20, the speed at which a spacecraft re-enters the atmosphere, they reach 10,000 degrees, hotter than the surface of the sun. The Space Shuttle's thermal protection tiles, the most advanced thermal shielding material publicly available, were designed for Mach 25 re-entry conditions. They worked by a principle called ablation, sacrificial material that chars and erodes, carrying heat away from the surface. Ablative material is single-use. An aircraft that must make repeated high-speed passages through the upper atmosphere cannot ablate its way to safety. It needs a fundamentally different solution. The X-15, which flew to 354,000 feet and Mach 6.7 in the 1960s, used a nickel alloy called Inconel X750 that could survive the thermal environment for the duration of its short hypersonic flights. But the X-15 was rocket-powered, made individual flights lasting minutes, and returned to land as an unpowered glider. An operational hypersonic aircraft, one that could fly repeatedly, carry payload, and return to base without being rebuilt, required solving the thermal problem in a way that neither ablation nor Inconel could provide. That solution, the classified thermal protection system of whatever aircraft currently operates in this regime, has not been publicly described.
Thermal survival is only one of the physics problems that near-space flight must solve. Propulsion in the near-space regime presents a separate and equally fundamental challenge. Conventional jet engines require oxygen. They compress incoming air, mix it with fuel, ignite the mixture, and expel the combustion products. At 100,000 feet, there is insufficient air to sustain this process. Rocket engines carry their own oxidizer. They can operate in a vacuum, but they consume propellant at rates that limit operational duration to minutes, not hours. The theoretical solution, known since the 1940s but only recently approaching practical implementation, is the Scramjet, supersonic combustion ramjet. A scramjet has no moving parts, no compressor stages, no turbine. It works by using the aircraft's own forward velocity to compress incoming air at the inlet, then igniting fuel in the compressed supersonic airflow without first slowing it down. Conventional jet engines slow incoming air to subsonic speeds before combustion. Scramjets maintain supersonic airflow through the entire engine. This is the physics breakthrough that makes sustained hypersonic flight theoretically possible, but it works only above approximately Mach 4. Below Mach 4, the compression is insufficient for combustion. Above Mach 4, it becomes self-sustaining. The transition between conventional jet propulsion and scramjet propulsion, the speed range between Mach 3 and Mach 5 where neither works efficiently, is called the hypersonic gap, and it is the engineering problem that has defined classified aerospace research for the past 30 years. The X-43A demonstrator, publicly acknowledged, flew at Mach 9.6 in 2004 on a scramjet for approximately 11 seconds. 11 seconds. What is currently classified, what the budget lines suggest has been funded continuously since the X-43A, is the development of sustained scramjet operation beyond proof-of-concept duration. The gap between 11 seconds of controlled scramjet flight and operational hypersonic capability is where the next generation of classified aviation exists.
The pattern in American aerospace history is consistent. The U-2 flew for 4 years before a Soviet missile proved its existence publicly. The SR-71 flew operationally for a decade before official acknowledgement. The F-117 flew for 7 years before a public airshow debut. The B-2 flew for 3 years before its existence was disclosed. In every case, the gap between first flight and public acknowledgement was between 3 and 10 years. The current classified aerospace budget contains line items that analysts have identified as consistent with hypersonic aircraft development at the operational level, not demonstrators, not proof-of-concept vehicles, operational platforms. The SR-72, the notional successor to the SR-71, has been mentioned in Lockheed Martin public statements since 2013. A Mach 6 aircraft, optionally unmanned, capable of reaching anywhere on Earth in 90 minutes. It has never been officially confirmed as an active program. The classified budget says something different. And the pattern of history suggests that whatever currently flies in the regime above 100,000 feet, in the altitude where wings do not work as wings are supposed to, where engines cannot breathe as engines are supposed to, where materials cannot survive at temperatures they are not supposed to reach, has been flying for years before anyone outside the program was allowed to know. The sky does not end where the blue ends. It continues into the black, into the regime where physics rewrites itself, and into the operational altitude of aircraft that the world is not yet supposed to see. Follow for more about the classified physics, the documented programs, and the budget evidence for what flies above everything you have ever flown in.